I spent a large part of my career working in industry, and a big proportion of my work has been mathematical modelling and using deterministic and stochastic models. So I should start by saying that when we talk about a model, we mean a representation of something, and usually it's some kind of process or some phenomenon that's taking place in the world around us. A very good example with which many of you will already be familiar are the kinematic equations. Now, they arise in particle motion in physics, and the results from these deterministic models can be quite accurate under idealized conditions. But it should be stressed that the conditions are ideal, and they can never be replicated in reality. So the model generates a number for us. In the case of v equals u plus at, it will tell us the velocity of a particle at a given instant in time when it starts with an initial velocity u and is subject to some constant acceleration a. So in the figure, you can see v equals u plus at illustrated as a straight line graph, the green line, and it shows u is equal to 0 and the acceleration I've chosen to be 9.8 meters per second squared. So v is uniquely determined at any given instant in time by the initial velocity u, which we've set at 0, and the constant acceleration a, which is 9.8 meters per second. In the case of this example, at t equals 5 seconds, the velocity is going to equal 5 times 9.8, which is 49 meters per second. If we were to represent this as a stochastic model, that is, a model which is subject to some kind of uncertainty, there might be random fluctuations in the initial conditions, in the initial starting velocity, and variability in the acceleration, we'd finish up with a probabilistic model. And as an example, I've given some stochastic parameters. So in this case, there are 3 parameters. And the first one is that the probability that u is less than 10 meters per second but greater than 0 is 0.2, and the probability that u is greater than or equal to 10 but less than or equal to 20 meters per second is 0.8. And I've also added the other condition that the acceleration varies with time, and it could be anything between 7 and 10 meters per second squared. So what we're saying then is we're not really sure what the initial velocity is, and the acceleration is no longer constant. It can vary with time, but we don't know what that acceleration is going to be at any given time, but we do know that it's constrained to be between 7 and 10 meters per second. So instead of getting a nice straight line, as we did with the deterministic model, we will get an envelope of solutions with different probabilities. And the upper limit of the stochastic model is given by the yellow line in the figure, and the lower limit is given by the red line. So at t equals 5 seconds, the velocity could be anywhere between the lower limit and the upper limit of the model. We can't say where it's going to be because the initial conditions are probabilistic, and the acceleration is somewhere between 7 and 10, and we don't know what it is or what it was. So what we can say then is that in the area which I've shaded a yellow colour just here, it's more likely that the velocity will be somewhere between 45 and 70 meters per second, because the initial velocity had an 80% chance at p is equal to 0.8 that the initial velocity was between 10 and 20 meters per second. Less likely is the case down here, although it's possible that the velocity could be between 45 and 35 meters per second at t is equal to 5. It's less likely. There's only a 20% chance that it will be in that range. So the big difference then between the probabilistic or stochastic model and the deterministic model is the deterministic model is precisely constrained and precisely parameterized, and we know that it has a definite value or a definite output from the model subject to the parameters and the variables involved. In this case, it's a function of time, and we know that at any given instant in time we get a definite numerical value for the velocity. However, with the stochastic model, when we measure it, or when we take the output from the model, the output is probabilistic. There's a possibility that the velocity could be in one particular range, and another probability that it could be in another range. So we don't have a definite answer. It's much more difficult to interpret the results of a stochastic model compared to the deterministic model. Later in the lecture, we'll look at some exponential growth and decay models. Exponential growth and decay models are deterministic, and when applied to populations, they can give us a rough indication of what the population might be at a particular time. In the model on the left side, we can see a population of rabbits and how it grows from the year 2000 to the year 2040. Starting off at about 14 million, it grows exponentially to around 50 million. The deterministic model is governed by an exponential law, which is a function of time. So at any given time, we have an exact value for the population. Of course, we should all realize that this is never going to be the case. We actually don't know with any accuracy or reliability what this population is going to be. A more realistic model would be a stochastic model, as shown on the right-hand side. As with the kinematic equation, the stochastic model has boundaries, or an envelope, in which the solutions would lie. So here we have an upper boundary and a lower boundary on the population growth for the rabbits. But with the stochastic model, we can introduce other factors that may significantly impact the population. So, for example, imagine that a fatal virus attacked the rabbits in 2014. We can see by the two dotted red lines the impact that this would have on the population. So, if the population were larger to begin with, it's much more likely to decrease very rapidly under the influence of the virus, because the more individuals there are, the closer they will be together, and the more rapidly the virus will spread, and the more of them will be affected by it in a short space of time. With a sparser population, and the rabbits are spaced further apart over the landscape, it might take longer for the virus to affect them. So the net effect on the lower population may be less compared to the decline that we'd see with a higher population. But again, even with a stochastic model like this, it would be very hard to compare our results to reality. If we consider quite a constrained case, such as the population of people in Astana, well, it would take us a long time to count them, and what do we define the population as being? Is it the people who are actually living in Astana at a particular moment in time? It can't be an instant in time, because we just wouldn't be able to count everyone in that instant. And assuming that it's going to take us quite a bit of time to count everybody, well, there's a good chance that some more people might have been born, or some people might have died in that period. So it's going to be in a constant state of flux. So we can never precisely or reliably say what the population is going to be. But we can say, well, it's about 750,000 in Astana, and maybe most people would not disagree with that. To summarise then, in deterministic models, all the parameters are known. In stochastic models, the parameters may be subject to random variations. The state of a deterministic model is always known. But in a stochastic model, it's never precisely known. In the deterministic model, every subsequent state of the evolution of the model depends on the previous state. But this is not the case in the stochastic model. It will not depend on what happened before. Deterministic models usually have an output that's relatively easy to explain and interpret, but this is much harder to do with a stochastic model. Also, deterministic models are generally easier to verify and compare to real-world observations, but this is quite difficult to do with stochastic models and the stochastic processes that they're modelling. Okay, now have a go at the multiple choice question.